Hello, I'm Guillermo Castilla, and this is AULA UE. We'll be talking about the discrete model known as binomial in this video, and in order to do so, first we have to describe the two variables of the binomial model. In one case we'd have n, and as the other variable we'll have p. N in this case and p will be the only two necessary ingredients for the model itself. N is the number of repetitions, and P is the probability of success of a certain repeated event. Okay, so let's explain it through an example. A certain game is won when rolling a single die once and you get a 6. Okay, so we play 4 times in a row. Here's a little die diagram here. So we're going to roll the die. If you get a 6, you win, and we're going to play 4 times. Okay, so let's see how many times do we actually repeat in this case. What does the variable describe? What is our chi, our random variable of the binomial model? Well, chi would be winning the game. Okay, so we've got a variable that describes the times we win the game. How many times can we win the game in this case if we play 4 times? Well, we can win no times, 0 times. We play 4 times and we lose all 4 times. Or the maximum chi can get up to is 4, because we can win the 4 times. But that's it. And the variable can only go from 0 to n. So what is the probability of chi being a certain number x in this case? Well, it's the Newton binomial n over x times p, the probability of success, to the power of n minus x, to the power of x, times q, which is the complementary probability of p, 1 minus p is q, to the power of n minus x. So this would be the factorial of n over the factorial of x times the factorial of n minus x, times p to the power of x times q to the power of n minus x. That would be the complete probability of chi being x. Okay, this is what we'd call the quantity function of the binomial model, which would be represented as f of x. So the probability of chi being x is f of x. For example, the probability of chi being 0, the probability of losing 4 times in this game. Okay, so first of all we'd have to describe the variables of our binomial model. The probability of success in this case would be 1/6, because you only win when you get a 6, which is 1 out of 6 possible rolls on the die. And since we're going to play 4 times, the number of repetitions, the n is 4. So we're going to play with a binomial for 1/6 in this case. So let's see what's the probability of chi being 0 in a binomial for 1/6. This would be 4 over 0, as you can see on the formula up top, times 1/6 to the power of 0 times 5/6 to the power of, we'd have to write 4 minus 0, which is 4, of course. So the binomial 4 over 0 is directly 1. So, and 1/6 to the power of 0 is also 1, so this is directly 5/6 to the power of 4, which is 0.4823, as you can see in this case. Of course, we'd have all the rest of the chi's. We could calculate the probability of chi1, chi2, chi3, and chi4. As I said before, this is what we call the quantity function. This is the f of x. So f of x is the probability of chi being x. Okay, there you go, quantity function. And of course, since chi can take the values from 0 to 4, we'd have quite a few probabilities. In this case, the chi equals 1 would be 4 over 1 times 1/6 to the power of 1 times 5/6 to the power of 4 minus 1, which is 3. And directly we'd get this 0.3858 number we have here. Okay, well, the rest of the probabilities in the problem, the rest of the possible calculated probabilities, are the probability of chi being 2, which is f of 2, the probability of chi being 3, which is f of 3, and the the probability, of course, of chi being 4, which is, as you can imagine, of course, f of 4. So next things next, we'd have to see how this turns up in the binomial model, as in the formula itself. We just put x as 2, 3, and 4 respectively, and n would still be 4 in each case, p would be 1/6 in each case, and q, which is the complementary probability of p, would be 1 minus 1/6, which is 5/6. So let's see how this turns out. Let's clear things up a bit on the whiteboard. See, get rid of this and get rid of that. Very well. Just this 4 left. Okay. And let's move all this to the left to have a little more space. Okay, much better. Now that we've got everything cleared up, we can get back to our model. Just to remember, since I've erased it from the screen, the binomial model we're working with is a 4 1/6, and in this case, since all the results we've got from 0 to 4, all the values of the binomial. If you take a look, this is 0.4, 0.3, 0.1, 0.01, and 0.008. If we add them all up, they add up to 1, which is the complete probability, because after all, this is a game, and what we're doing is we're calculating all the possible results we can have. So what we're seeing here in this case is that the probability of winning 0, 1, 2, 3, 4 times is the complete probability we have in the problem. As you can see here, we're representing the quantity function graph, which is a graph that goes from 0 to 4, all the values of the possible variable. And as you can see, in this case, it starts in 0.48, then 0.30, well, this would be rounded up to 39, 0.12, in this case over here, then 0.02, and well, this one would be practically 0 because it's 0.0008, 0008. So as you can see, all this function all the way down really represents the model itself, the binomial model. If we add them all, it has to add 1, because you know the probability always goes between 0 and 1. And this is the step-by-step representation of the quantity function, the f. Of course, we also have the other function, which is the distribution function, the capital F, which would just be a summatorium from k equals 0 to x of n over k to the times p to the power of k times q to the power of n minus k. As you can see, it's the same as the quantity function, but just substituting the x for a k and doing a summatorium from 0 to x. The number that would give me the maximum probability in this case would come out of multiplying n times p. In this case, if you see n is 4 times p, which is 1/6, is smaller than 1. So the x of maximum probability is 0. We can actually see that the x of maximum probability is 0 if we just look to the left of what we have on the board, where it says 0.4823 as the maximum probability. Since it has to be a natural number because we're talking about a discrete variable, now I put the natural number asterisk because it really does include the 0. Well, in this case we can see clearly that it would be 0. So I hope you find this useful, and I'll see you around soon enough. Goodbye, and thanks to all.